This lab is called the Target Stoichiometry Lab. And in it, we're going to conduct a reaction twice. We're going to do a little board work. And then we're going to very carefully measure out the second time we perform this reaction an amount of the reactant so that we can get a target amount of the product. That's why it's called target stoichiometry. Now, the basic reaction consists of taking some baking soda, sodium bicarbonate, and simply heating it vigorously in a test tube. And the first part of this lab is simply going to ask us to perform the reaction and make sure that we get the products that we expect. We'll do a confirmatory test involving universal indicator solution, which will turn various colors based on the pH of the product that is found. So I have here a card showing what color the indicator solution ought to turn based on the pH or acidity and basicity, which is a topic we'll get to later in the year, of something that is produced. So following the procedure, I'll turn on my scale and I'm going to record the mass of a clean, dry test tube. So putting this on the scale, I got 19.62 grams. It then says in the procedure, scoop approximately 5 grams of baking soda. And you might say, well, my scale is good to the hundredths of a gram. Why would you say approximately 5 grams? Because anything in that ballpark is fine. But it should be somewhere around 5 grams. We'll precisely weigh it out, but it's got to be ballpark 5 grams. So I happen to know roughly what 5 grams of baking soda looks like. About that much. And I'm going to put my test tube back on the scale and record the new volume. I've got 24.43 grams now. Okay, so I've got approximately 5 grams, very close to 5 grams. And I'm going to begin the heating process. So to do this, we're simply going to take a ring stand, ring clamp, or test tube clamp, and insert the test tube, tighten the valve, and then we're going to light a Bunsen burner and heat it vigorously. You always put goggles on for that. So I'm going to turn the gas on, light our flame, and according to the procedure, I want to adjust the flame so that the bottom part of the test tube is in the hottest part of the flame. The hottest part of a Bunsen burner flame, interestingly, is the tip of the indigo. So there's an outer flame that's kind of a darker blue and an inner flame that's indigo. The tip of the indigo is where you want to make sure whatever it is you're heating goes. Okay, so it says heat gently for about 10 minutes. During the heating process, do these 2 steps. Number 1, we're going to watch the upper half of the test tube. Now, I can see this happening right now, but there are a little bit of water condensing. What I'm going to do is bring you closer here so you can get a good look at this. If you look closely at the top portion of the test tube, like right around here, there's condensation. That tells me that by heating this baking soda, I'm actually producing some water as a product. The other thing that we're supposed to do during the heating process is take a Q-tip, a little Q-tip, and we're going to put a drop of indicator solution on it. Yeah, maybe more than a drop. Let's see here if I can get a little more. Actually, here's what I'm going to do. Just get a little bit of this. Okay. So what I did is I dipped the tip of my Q-tip into the indicator solution. And then I'm going to insert my Q-tip into the mouth of the test tube. And I'm going to look for some color changes. Now, at first, the indicator solution was perfectly blue, like a dark blue. But as you can see, upon inserting it, it's gotten more orange than it had been before. And If I insert it a little more, it gets even more orange. Now that tells us something. That's an important piece to this lab. Here's my color card showing what color the indicator solution should turn based on various pHs. Now, as you can see, the orange color, so I'm estimating here, but it looks like it's roughly this color, was a pH of 5. Now, 7 is neutral. 5 means we've got something that's acidic. Now, if you read your lab report, I'm in step 5, part B here. If the pH goes down below 7, you have made an acidic compound in the test tube. And that evidence is presence of a non-metal oxide. So in this reaction that we're performing right now, we've got a non-metal oxide along with some water that's been condensing on the inside of the test tube. I'm going to let this process continue to heat, and then what I'll do, and I don't think I need to keep you on the video here, so I'm going to pause it, but we'll let it heat for the remainder of the 10-minute heating period. Then I'm going to let it cool down, and then I'm going to weigh it on the scale once again, and we're going to note what changes in terms of the mass. We'll do some board work, and then we're going to come back and perform the reaction again with the idea of producing a target amount of the product. Okay, so pause for board work now. So now in the target stoichiometry lab, we've completed part 1, the confirmatory tests. We need to do a little bit of calculating before we can go on and do part 2, where we're actually using our idea of a target stoichiometry lab. Based on what we had recorded in part 1, the mass of the empty dry test tube, 19.62 grams. The mass of the test tube with some baking soda in it, 24.43 grams. When we observed the upper half of the test tube as it was being heated, we saw water vapor condensing on the top half of the tube, meaning that water would have been one of the products. What color did the indicator solution turn? So this was that dark blue fluid that we put on a tip of a Q-tip, and it turned kind of an orangish color, which, based on our pH card, means that our pH was about 5, meaning below 7, and that's in the acidic territory. I then paused the video, completed the heating process, and recorded a final volume of the test tube with powder in it of 22.48 grams. We're going to use that data going forward in our calculations. Part 1. We're just going to take the word equation based on the description in the introduction to the lab. So in the intro, the first sentence, when heated gently, sodium bicarbonate, also known as baking soda, decomposes into water vapor, carbon dioxide gas, and solid sodium carbonate. Just reconstructing or deconstructing that sentence, we've got sodium bicarbonate, also known as baking soda. That's the lone reactant in a decomposition reaction. And we make these 3 products: sodium carbonate, carbon dioxide gas, and water vapor. Let's use our knowledge of chemical nomenclature to translate names into formulas. On the periodic table, we know where sodium is. You can look on any periodic table, you'll see it's a column 1 element, and it's forming an ionic compound in sodium bicarbonate with bicarbonate ion. Now, the polyatomic ion was given to you in the analysis questions. It's HCO3 with a 1- charge for bicarbonate. So what we'll do to write the formula is crisscross those charges. Take the size of the positive ion's charge and write it as the subscript for the negative ion, and vice versa. Size of the positive ion's charge and write it as the subscript for the negative ion. I might write out initially the subscript 1, but when you neaten up the formula, typically we don't even write a subscript 1. And if nothing's written outside of a set of parentheses, you don't need to write the parentheses either. So Na1 HCO3 simply becomes NaHCO3. Okay. Sodium carbonate. Again, we see sodium ion, and again, it's going to carry a +1 charge. Carbonate ion is another polyatomic ion that was also given to you in the analysis questions. They gave it as CO3 with a 2- charge. And if we crisscross those charges, this time we would get Na2, because the size of the carbonate ion's charge is 2. And then initially, I always put the polyatomic ion within a set of parentheses, and the size of sodium ion's charge is 1. So it becomes Na2, and then parentheses CO3 1. Well, if it's a 1 subscript, you don't need to write it. And then if nothing is written outside of a set of parentheses, don't even write the set of parentheses. So our equation is starting to shape up here. We've got NaHCO3 yields Na2CO3. Carbon dioxide. Here is a covalent compound, binary covalent. We use prefixes to indicate the number of atoms. This one's pretty straightforward. If you remember, the prefix di means 2, then it's simply 1 carbon and 2 oxygens, plus you've probably heard carbon dioxide a million times. It's CO2. And lastly, water. Well, by golly, you better know that water is H2O. Okay, so we've got our unbalanced equation. Now let's balance it. We do need a coefficient. Where does the coefficient go? Pay close attention to the carbons. On the right side, there's a carbon here and a carbon here. But on the left side, there's only 1 carbon. So I'm thinking, okay, we've got to do something about the carbons. Also, you might note that there are 2 sodium atoms on the right side and only 1 sodium atom on the left side. So what if we put a coefficient 2 in front of the baking soda, the sodium bicarbonate, and see how that balances out? Now, if we count up atoms on either side, we've got 2 hydrogens, left side, right side. We've got 2 carbons, left side, right side. In total, the oxygens are a little tough. There are 6 oxygens, 2 formula units of sodium bicarbonate, each of which contain 3 oxygens. So mentally, I'm thinking 6. And then on the right side of the equation, we've got 3 in sodium carbonate, plus another 2 in carbon dioxide, plus another 1 in water. That's 6. And then lastly, the sodium atoms balance because there's 2 of them on either side. So now we've got our balanced chemical equation. This is going to be important. We'll need to come back to this later on. All right. Now for some of the math. In question 2, they ask us, what mass of baking soda was initially present? Well, based on our data table, we had a mass of baking soda in the test tube of 24.43, and we'll subtract from that the mass of the empty dry test tube. And so I'm just going to pull out a calculator and punch these numbers in. We get 4.81 grams of baking soda. Next, they want us to calculate moles. This is a good exercise for our stoichiometry unit because we've got to figure the molar mass. Okay, so if in this formula, baking soda, we've got sodium, hydrogen, carbon, and oxygen, and there's 1 atom of each type except for the oxygen, which has 3 of them. I'm looking up on the periodic table the atomic weight for each of these elements and rounding to the 10th place because we don't need to carry it out to too much detail, or rather the level of precision beyond the tenths place is unhelpful. And so we get, if you punch these numbers into your calculator, we would get 84 grams per mole. Okay, so we've got a mass of 4.81, and we've got a molar mass of 84.0. So we're simply going to set up a conversion factor where we'll be sure to cross out number of grams. So it's 84 grams equal to 1 mole. And the way that I set up the conversion factor ensures that the unit grams crosses out. So the only thing that doesn't cross out is the unit moles, which is what we need to come up with in the answer. So I'm going to type in my calculator 4.81 divided by 84. And we get a pretty small number here, 0.0057 moles. That's okay. It's okay to have a small number. Question 4. Based on your balanced equation, how many moles of sodium carbonate would you expect to produce? So we have this many moles of baking soda, 0.0057 of NaHCO3. Now they want us to write a conversion factor enabling us to get to moles of Na2CO3. In that balanced equation, remember there was a coefficient of 2 in front of the baking soda. That's a really, really important thing. Let me slide this back here. This coefficient 2 matters. And the coefficient implied in front of Na2CO3 is a 1. So it's a 1-to-2 ratio of baking soda to sodium carbonate. And I'm going to write that so that the moles of the baking soda, NaHCO3, crosses out, meaning that's going to go in the denominator. So if you follow the units, moles of NaHCO3 crosses out. And on my calculator, I'm going to take 0.0057 and divide that by 2. And I get 0.0. I'm going to round to the 2 digits, 2 significant figures here, 0.029 moles of Na2CO3 expected. Then we'll use this number and our molar mass of sodium carbonate to figure out grams. Okay, so now we've got another molar mass calculation. In this formula, there are 2 atoms of sodium, 1 of carbon, and 3 of oxygen. And I'm using atomic weights from the periodic table, rounded to the 10ths place. And I'm just carrying out that calculation. So 2 times 23 for sodium, that gives us 46. 1 times 12 for the carbon. And 3 times 16 gives us 48 for the oxygen. That adds up to 106.0 grams per mole. All right. If we're expecting 0.029 moles, and we've got an atomic weight, or excuse me, a molar mass of 106, then we'll simply multiply. So 0.029 moles. And if we know that for every 1 mole, we have a mass of 106 grams, the unit moles will cross out. And I'll punch that into my calculator, 0.029 times 106. And I get 3.03 grams of Na2CO3 expected. Question 6. So we have our expectation. Question 6 says, how many grams of Na2CO3 did you actually get? Now let's revisit this. In our data table, the mass of the test tube and some powder in it after heating was 22.48 grams. If during the course of heating we drove off all of the water, in water vapor, and all of the carbon dioxide that we could have, then the powder that's left in the test tube after heating is no longer sodium bicarbonate, it should be sodium carbonate. So to figure out the mass of sodium carbonate we actually got, we'll take the mass of that powder in a test tube minus the mass of the empty test tube. So we'll take 22.48 minus, presuming the mass of the test tube didn't change, which I don't think it would have. We have no reason to believe that the test tube changed. We would get 2.86 grams of sodium carbonate, which, by golly, students, take a look. Your expectation was 3.03, and what we actually got was 2.86. That's pretty close. Question 6 says, how close was your expectation to the prediction? I would say that's extremely close, a remarkably accurate result. Question 7, this is the really good one. Suppose your goal was to produce exactly 2.00 grams of sodium carbonate after heating the test tube. How many grams of baking soda should be added to the test tube initially? Knowing what we know, so we've got the molar mass of sodium bicarbonate, we've got the molar mass of sodium carbonate, we even have a balanced equation. To calculate this last one, for number 7, we're going to need a little bit of space, so I'm going to erase some of our prep work here. In number 7, we want specifically 2 grams of sodium carbonate, 2 grams of the product. And the question is, how much baking soda should we put into the test tube initially in order to get this out at the end? Well, this is going to be a mass-to-mass conversion. We've practiced these in class, but here we get to do it IRL. So the first conversion factor will allow us to convert between grams and moles. So we need to use the molar mass of sodium carbonate, which, if you remember, was 106 grams per mole. Next, we'll use the mole ratio from the balanced equation. We had already established earlier that it was a 2-to-1 ratio in the balanced equation. That's going to come into play again. And then the third conversion factor will enable us to convert between the number of moles of baking soda expected or required to the mass of baking soda required. And if you remember, that was 84 grams per mole. Now, the key is going to be to set this up so that all the units cross out. If we begin with the unit grams of Na2CO3, I want to make sure that that same unit, grams of Na2CO3, appears in the denominator. And if you remember, the molar mass was 106 for every 1 mole of Na2CO3. Next, let's look to the molar ratio in the balanced equation. It's 1 mole of sodium carbonate for every 2 moles of baking soda. Let's make sure to write that with the 1 mole in the denominator of Na2CO3 and the 2 moles in the numerator. And then lastly, the molar mass of the baking soda was 84 grams per mole. We'll write this so that the unit moles is in the denominator and thus can cross out, and the unit grams remains in the numerator. So follow the units. Grams of Na2CO3 crosses out. Moles of Na2CO3 crosses out. Moles of NaHCO3 crosses out. The only unit that doesn't cross out the way we have this set up is grams of NaHCO3, which is what you want as your final answer. Now, for the calculator part, multiply all of the numerators together and write down that result. So let's do that. I'm typing in 2.00 times 1 times 2 times 84.0. I get a result of 336. Next, we'll multiply all of the denominators together. 106.0 times 1 times 1. Since anything times 1 is just that number, then we'll simply write that number down. And then lastly, take the numerator result divide by the denominator result. And we get 3.1, I'm going to round to the hundredths place, 3.17 grams of NaHCO3. Okay, now that we've got that, we're going to measure out this amount into a test tube, carry out the heating process again, and see how close our result is. Did we actually get 2 grams of the baking soda, or 2 grams of the sodium carbonate based on the 3.17 grams of baking soda? Here's the fun, and this is why we call it a target stoichiometry lab, is that we're actually looking to get a quantifiable amount that we expect. So now we're back to the bench here, and we're going to do another heating round, knowing now that we want as our target to get 2 grams of sodium carbonate, and we've calculated that we should weigh out 3.17 grams of baking soda to get that. We're going to take a new clean, dry test tube, and we're going to weigh it on our scale. Wait for it to turn on. Set it down on the scale, and I get 18.98 grams. In order to add precisely 3.17 grams of baking soda, and we don't need to be super meticulous about this, but if I take 18.98 and add 3.17 to it, I want to get 22.15 grams in total. So if I scoop some baking soda, I want to aim for 22.15 grams. And I have a rough approximation of how much that'll take. That's actually really close, just need a little more. Oops. Okay, perfect. So I got 22.18 grams of baking soda. That's really close to our the amount of baking soda I was hoping to get, which was 22.15. Let's say that last 0.03 of a gram is negligible. Okay, so massive test tube with baking soda, 22.18. Now, we'll put our test tube into the heating apparatus. We'll put our goggles on, set aside our scale and baking soda, turn the gas on, and just like we had done before, we're going to heat the baking soda vigorously for about 10 minutes or so. And we should still see, in the lab procedure, it doesn't ask you again to look for evidence of water vapor, although that's easy to glance at and see evidence of, nor does it ask you to take the indicator solution and stick it in the test tube, because we've already done that. So we're simply going to let it heat for 10 minutes. I don't need to show that on the video, but after 10 minutes of heating, I'll let it cool down. I'll weigh it one more time, and then we'll go back to the board once again to do our final calculation. Okay, students, now we're going to wrap up our lab report for target stoichiometry. In part 2, we had an initial mass of the empty dry test tube of 18.98 grams, a mass of the test tube with baking soda of 22.18 grams. That's roughly an adding of 3.17 grams of baking soda. And then we heated it and after the heating, the baking soda became sodium carbonate, and we ended up with 20.34 grams. Analysis question 8 asks, what's the mass of the sodium carbonate we produced? Well, after heating, our mass with the test tube was 20.34 grams, and we'll subtract from that the mass of the empty dry test tube, 18.98. That gives us 1.36 grams of baking soda produced. Was that close, is question 9. Was that close to the 2.00 gram target? Not especially. It's not horrible, but it wasn't an especially close result. We were targeting 2 grams. We got something fairly significantly less than that. You could, if you wanted to, calculate a percent error with the expected as the accepted value and the observed as the observed value. But I'm not asking for that specifically in this lab report. So we got something, fairly different, and we'll talk about that in a later question. Question 10, look at the observations for the upper half of the test tube you had recorded in data table 1. Which of the products of this reaction do you have evidence for? Well, if you remember, it was water vapor condensing. So the evidence of that water vapor was the condensation on the test tube. 11, look at the pH of the test tube you recorded in data table 1. It was acidic. If you remember, the indicator solution turned orangish in color, which indicates acidity. And that's evidence of a non-metal oxide. Non-metal oxide. Well, students, CO2 is a carbon, is a non-metal, and when it's paired with oxygen, it's called an oxide. Hey, we got evidence of CO2 vapor being given off during the course of the reaction by that change in the indicator solution's color. And then question 12, describe in detail a source of error. Why didn't we get exactly 2 grams as in our result? Well, numerous things could have happened. Most specifically, I would suspect an incomplete reaction. If not all the baking soda got converted into sodium carbonate, well, that would explain a lower than expected mass because there's a mole ratio and a difference in the molar mass of the sodium carbonate and baking soda. Other things, so besides incomplete reaction, perhaps, let's see, if the heating wasn't vigorous enough for whatever reason, the Bunsen burner flame, again, that kind of gets to an incomplete reaction, but that's probably your best bet as to why we got numbers different from what we expected. Thank you very much for your great work. This was kind of a detailed lab, a good one, a crucial one for understanding reactions in stoichiometry. So I thank you for your good work. We'll see you next time.